All right, so we're going to do a quick review of electrochemical cells. What electrochemical cells are, they are apparatuses that use a spontaneous chemical reaction in order to generate energy or do useful work. Usually that useful work is in the form of electricity. So one of the ways you can tell that you have an electrochemical cell is that there is a division in the two halves of the cell. So normally these are done in beakers. They don't have to be done in beakers. There are other configurations, but often we see these in beakers. And in the beaker we will have an electrode, and it's usually made of some metal. It doesn't have to be metal. Carbon works quite well. The electrodes sometimes can even be inert. If you're going to use hydrogen, as one of the electrodes, you can put an inert piece of platinum in there and bubble the hydrogen past it. But normally they're metals. And we can pick any metals we like, actually. So let's have a couple of metals to put in our electrochemical cell. Silver, okay, we're going to make a nice expensive cell here. We're going to use solid silver on one side.
Let's use gold on the other side.
And gold. So spare no expense. We're going to use silver and gold as our electrodes. Now we need an aqueous solution to surround the electrodes. That'll help carry the current, and you'll see it's really necessary for the ion formation. Yep.
Silver nitrate.
We use silver nitrate. Good choice. Why is silver nitrate a good choice?
Because nitrate solutes everything.
So that's AgNO3 aqueous. Why is silver nitrate a good choice? Yes?
Because nitrate is soluble with pretty much
Yeah, so you put a soluble compound. We don't want to put silver chloride in there because we won't get a good concentration of silver in the solution because silver chloride is insoluble. And not only that, nitrate in particular is reactive, so we want something there that's not going to oxidize or reduce. We're interested in mostly oxidizing and reducing our metal electrodes. What solution can we use on the other side?
Okay.
Gold nitrate will do.
Why did you go the opposite direction? Sulfate. Sulfate is like... Sulfate kind of dissolves.
Some gold nitrate.
No, not gold.
And I think we've got some gold +3 in our chart. So if we've got gold +3, we're in good shape. Alright, so, and this is all aqueous. So we have AuNO3 taken twice. And we've got some AgNO3 aqueous, and we've got our electrical cell ready to go. Do we have gold 3+ in our chart? Great, so we're going to use that because we'll get a potential for it. Now, obviously the electrons are going to go from one electrode to the other electrode. We need to figure out which electrode they're leaving from and which electrode they're going to. Not only that, we want to give them a way to go, so we will put a wire connecting them, and we'll connect it to a voltmeter so that we can read the voltage, the potential difference that's encouraging the electrons to move as they go from one electrode to the other. Alright, now we're ready to figure out what's going on in our cell. There's one more ingredient we need to put in our cell, but we'll talk about that in a minute. Let's just figure out what voltage we're going to get from our cell now. In order to figure out the voltage, we'll have to figure out what the electrons are doing. What element are they leaving, and what element are they going to? What are our possible reactions? And let's consider our reduction reaction first. So our possible reduction reaction. Yes. What's our possible reduction reaction?
gold 3+ plus 3 electrons reacts to make solid gold.
Alright, and what's our reduction potential for that reaction?
1.50 volts.
Alrighty. What other possible reduction reactions do we have? Yes? Right on. And what's our reduction potential for that?
0.80 volts.
0.80
volts.
volts. All right, so it's a powerful reaction, but not as powerful as the other one. Are there any other possible species present that might be reduced? Water is present. Do we have a reduction reaction for water in the chart?
No, you should.
Are you sure?
I don't think that's Jesus was acceptable.
Okay. Any other species present?
Okay, I got that one.
Nitrates.
Do we have a reduction reaction for nitrate in the chart? All right, so Dave's assured me that we've got neither a reduction reaction for silver for nitrate or for water.
Then it's not really possible to reduce nitrate because it's already.
Well, if it already has a negative charge, but sometimes things with a negative charge can be further reduced. Take, for example, this reaction here, which I'm getting out of the chart. Is this not a reduction of nitrate?
Whoa.
And it is in the chart, right? So we do have a reduction reaction. This won't take place because we don't have any hydrogen. So nitrogen, even though it's negative, nitrate, even though it's negative, can be reduced. If this was an acidic solution, we would get a reduction of the nitrate. So you've got to check the solution. If this is just ordinary nitrate, then no. But if it was acidic, and you would be keyed for that in the question, it would say acidified silver nitrate. And that means acid is present. So they'd have to tell you that acid was present, or they would have to have an acid present in the formula. So if this equation said, if this had something like HCl or something as well that was an acid, then we could get this reaction going. Okay, so be careful of that. If the ingredients for a reaction are present, then it would happen. And as it turns out, there is a reduction of water, so we did look very carefully in our charts. There is a reduction reaction for water, and it produces hydroxide and hydrogen gas, and it has a potential of negative 0.41 volts. So we did get a reduction reaction when we looked carefully for water. But the only nitrate one I've got is one that requires acid. If we don't have acid, we're not going to get that nitrate. We've got two nitrate reactions here, actually. But both of them require acid, so we can't have them. Okay? So you have to be careful with your chart. Now, of these possible reduction reactions, which one will take place? Why?
Because it has the most of the volts.
Yeah, it's the most favorable. It has the highest reduction potential. Yes?
Couldn't we have done possible oxidation reactions and just put the chart?
Yes, because we've already listed everything that's present, we could do oxidations. Now, we have two more things though we have to consider for possible oxidations that aren't in our chart so far. We've talked about our silver plus, our nitrate minus, our gold plus, and our nitrate minus. We've also talked about water, because these are aqueous solutions, so they're all in water. But if we're considering oxidations, there's two more things we have to consider that might be oxidized. What other things might be oxidized?
The solid?
Yes, the solid. So for oxidation, we also need to consider that the solids might be oxidized. So we might be oxidizing gold metal, and we might be oxidizing silver metal. All right, so we need to look at our chart and see what it is to oxidize gold and what it is to oxidize silver. Wait a minute. We already got that, don't we?
It's going to be negative.
It's the same reaction backwards. Okay, so oxidizing gold to give us gold, 3 plus and 3 electrons is negative 1.50 volts. It's the same reaction backwards, so the voltage has changed. Oxidizing silver is going to get us negative 0.80 volts. The negative means it requires this. much potential to make the reaction go. So these aren't favorable, and that's why the voltage is negative. These ones are favorable, and that's why the voltage is positive. Can we reverse this reaction? Well, no. This reaction doesn't apply reversed. Why? We can't just reverse this and say, oh, this is how we oxidize water. Why?
Because you don't have any products.
Yeah, this is not what we have to go forward to make water. But we need something where water is being oxidized. Do we see a reaction where we can oxidize water? Do we see a reaction where we can oxidize water?
Oh, one that involves. Oh no, I need an acid for that one.
Can you guys see that Sorry? Do we have a reaction where we can oxidize water? Yes, water will oxidize. What's our reaction for the oxidation of water?
Water turns into half
A half mole of oxygen gas, and we get some hydrogen ion, and we get 2 electrons out of it. And what's the oxidation potential for this?
negative 0.82.
Negative 0.82. There's another reaction for oxidizing water, but do you see that it's even more unfavorable than this one? Because in the forward direction, it is 1.23 volts. So in the reverse reaction, it's going to be negative 1.23. This is our most favorable oxidation of water. Okay?
I can't find the other one.
Close to the top, look for 1.23 volts. So just look for a positive 1.23 volts. That's water as well, but when we turn that around, it's
Even lower.
negative 1.23 volts, so it's less favorable. This is the most favorable oxidation we have. Right? It's not, the other one isn't going to happen before this one happens because it's even less favorable. All right, so we just decided that, well, wait a minute, we can't oxidize water. It costs energy, and turns out we have something that's a smidgen more favorable for the oxidation. What's more favorable for the oxidation?
The solid silver.
The silver, right? It's just a little bit more favorable, so it happens. Close though, wasn't it? It's very possible for a cell, for water to be what reacts, even though you have metal electrodes there. If water is the most favorable reaction, absolutely, it'll react as well too. So, we've got our reduction reaction, and we have our oxidation reaction. And we're good to go. Yes?
If we know that if we know that gold is the one being reduced, we automatically know that silver is the one being oxidized, correct?
No, it could have been water.
Okay.
If this had been 0.84, it would have been water, so we don't know for certain. In that case, the silver would have been an inert electrode, and the water molecules would come to the silver in order to give up their electrons, and the silver won't react. So that happens a lot. Well, we often use carbon electrodes for that. The molecule will float to the carbon, give up its electrodes, but the electrode itself doesn't have to react. And we can use platinum electrodes for that too, because platinum is very unreactive. So the molecule that's being oxidized or reduced can float up to the platinum, give up its electrons or gain electrons, and the platinum itself doesn't react. All right, so now we have to assign anode and cathode to this. Yes?
The reduction is the cathode.
Red cat. Reduction occurs at the cathode. So this must be our cathode. So this here is our cathode reaction. Okay? And that means that the electrons are going
To the right.
That means the electrons are going this way. They're going towards the cathode, always, always. Okay? So this is our cathode reaction, because it's our reduction. And this then must be our anode reaction, because it's our oxidation. So we got our cathode reaction, the reduction of gold, and we have our anode reaction, the oxidation of silver. So we started with gold and silver, and it turns out that we can reduce them. What is the overall voltage for this cell? We gained 1.5 volts by reducing gold, but we had to spin 0.8 volts in order to oxidize silver, so
0.7 volts.
so we get 0.7 volts out of it. Not the world's best battery, but it would work. It would work. Okay?
What about the cell bridge?
Yes. Okay. So now we have to get to our next discussion. And this is a little bit new because we didn't cover this last day. Okay. Let's consider what happens as we run our cell. So we connect everything, and we notice that the electrons leave the silver, and they travel through the wire, register 0.8 volts on our 0.7 volts on our voltmeter, and then arrive at the gold. When the electrons arrive at the gold, what do they do? Yes?
They coat the gold.
Yeah, the electrons arrive at the gold, they join a gold ion and make solid gold. Okay? So what we see happening is these gold ions in the solution are going to migrate to the source of electrons, right, being attracted to it, arrive there, get an electron, and suddenly you're solid gold and condense on the gold electrode. So in fact, if we had a solution of gold, we could actually purify gold, right, out of this by just attaching it to an ingot of silver, because the gold would come out of solution. It's not how gold is purified, but it could be. We actually speed the process up a bit, but that's the next lesson. So as with this reaction goes, this electrode will get bigger. Why does this electrode get bigger?
Because the gold in the solution is gathered.
The gold that comes out of solution and joins it, so you make more gold atoms. The electrode gets bigger. Now, what is happening to the solution as we pull gold atoms out of it?
Lonely nitrate.
Yeah, think about it. This solution was full of gold ions and nitrate ions, equal charge, right? So there are 3 nitrate ions for every gold ion, and we just reduced the amount of gold ions. That means we're having excess of nitrate. This cell would run for a fraction of time, like a fraction of a second, and then the electrons would stop moving. Why? The electrons would stop coming down the wire.
Because there's no more gold left in the solution.
Nope, there'd be lots of gold left in the solution. We packed that solution full of gold. Yes?
There's no more silver.
No, we put a big chunk of silver, so that's not a problem.
The nitrate repels the electron.
If we take away the gold, we're left with nitrate alone, aren't we? This means this solution ends up being negative. The electrons are not going to approach a negatively charged solution. They're repelled. So this, as written, this cell would run for a fraction of a second or so, and then it would stop running, because as soon as a few gold ions join the cathode, the solution becomes negatively charged. And we know 2 things in chemistry. Number 1, negatives repel negatives, so they're not going to go there. Number 2, we can't make a solution with a single charge. Right? It can't be done. So as soon as the solution is just a little bit unbalanced, this comes to a halt. Okay? So we need to solve that.
And they're like, that's not real. That's not real.
On this side, we have a similar problem. What is happening in this cell, in this half cell, as the reaction proceeds?
Nitrate is giving up its electrons.
The,
Nitrate is giving up its electrons.
what's giving up the electrons?
Yeah, silver.
The silver is giving up its electrons. So as this reaction proceeds, we'll see the silver begin to wear away. we start to lose silver. It'll pit, and then sections of it will eat away, and if we're unlucky, it'll make a break and fall down, and our cell will very quickly disintegrate. Because the silver, on this side, the silver atoms are leaving the metal to become silver ions. So what's happening to the charge in this solution? What's happening to the charge here?
It's becoming positive.
It's becoming positive. The electrons are leaving, right? You're leaving negative charges from one side to the other side. Well, if that happens, then this becomes more and more positive. So we have a problem. We have one solution becoming more and more negative because we're taking the positive charges out of it. We have another solution that's becoming more and more positive because we're dumping positive charges in it. All because we're taking electrons from one side and only electrons from one side and putting them on the other side, right? We're not taking whole species. We're taking just the electrons. So this side ends up with a deficit of electrons, and this side ends up with a surplus of electrons, and our cell stops working because the electrons aren't going to leave a positive charge behind and approach a negative charge. Electrons aren't going to do that. So we need to solve that problem. We need a way for the solution to replenish its charges.
But precipitate.
Well, to precipitate them means we would have to add some soluble ion. We would be adding a positive and a negative. One of them will precipitate and our solution would still be unbalanced. So precipitation reaction cannot help us. What can we do? A salt bridge. Someone's read ahead. Here's what we do. We put a solution in the middle where the salt in that solution can donate positive ions when necessary and negative ions when necessary. And here's how we do it. We take a tube and we put the tube in both solutions. So we take a U-shaped tube. We stuff the edge with like cotton wool or something that's permeable, but so that the fluid doesn't just fall out. So we stuff cotton wool or something, and I've even done it with paper towel. Couldn't find any cotton wool, you just use a paper towel, stick it in the end. And inside this tube is a solution, a salt solution. Because it's a salt solution inside this thing that bridges the tube, the name for it is a salt bridge. So don't picture a bridge made of like sodium chloride, okay, like I guess is the main, which there are actually existing in this world. In this case, this is just a salt bridge because it has salt inside it. So we call this a salt bridge. And it's a salt bridge because it bridges the two solutions, and inside it is a salt. And it doesn't matter what salt we use as long as it is soluble. You don't want to use something that's going to interfere with your reaction. So don't put, like iron nitrate or something in there because iron itself is going to want to gain or lose electrons, and that will mess yourself up. Can we think of something which is salty but relatively inert?
Lithium nitrate.
Okay, or table salt, right? Salt. Right? So sodium nitrate works. Sodium salts are excellent because sodium is relatively unreactive. Once it's given up its electron, it doesn't care to do anything else. And it's highly soluble. So I'm going to use sodium chloride because it's a salt bridge. I'm going to use salt. So it's a bridge that's got aqueous sodium chloride in it. How does it work? Well, it helps by releasing ions. So floating out, so inside here are sodium ions, Na plus aqueous, and chloride ions, Cl minus aqueous. Because they're aqueous ions, there's ions floating in there. What will migrate out of the salt bridge on this side, where we are making more positive charges?
Chloride.
The chloride. So the chloride will sense the positive charge, and the chloride will come migrating out into the solution to balance the positive charge. At the same time, what will come migrating out of the tube on this side? The chloride. And if you use nitrate, then it's great as well. Sorry?
The silver.
Sorry, the sodium. The sodium, sorry. The sodium. It's probably hard to see. But we're putting more sodium in this side. Right? So do you see that it'll go charge for charge. When one silver is made, one chloride will come out here. Right? if 3 silver are made, 3 chloride will come out here to balance those extra 3 charges. If 1 gold is made, 3 sodium have to come out, or 3, sorry. Yeah, if 1 gold is made, so you make a solid gold, you reduce the positive charge by 3, 3 positive charges will come out into the solution to replace it. So the function of the solid bridge is to keep the solutions electrically neutral. So what this salt bridge does is it releases positive ions when it needs to keep the solution electrically neutral, or it releases negative ions when it needs to keep the solution electrically neutral. Alright, so let's review. What's an electrochemical cell? Electrochemical cell is this apparatus that we use in order to get useful work out of an electrochemical reaction. What does this apparatus have? This apparatus had an electrode in a solution on one side, and on the other side it had an electrode in a solution. We used 2 different metals for the electrode. In our case it's gold and silver, it could have been copper and lead, it could have been iron and zinc, any 2 metals work. Okay? And even some non-metals will work as well too. Okay? Hydrogen will work, carbon will work for these electrodes. The electrons will leave one electrode and travel to the other. We can tell which way the electrons go by testing all the reactions that are possible and seeing which one is more favorable. So we know that one of the reactions will be a reduction. We check these metals and these solutions for possible reduction reactions, and we do that by checking the values in the chart. So if I had an iron electrode, I would look for reduction reactions involving iron, or for an iron solution. If I had a copper solution, I would look for reduction reactions involving copper. So you check the solutions and the electrodes for which reaction is most favorable. And the most favorable reaction happens, always. Yes?
Is it the the bigger number?
The biggest number for the reaction you're looking for. So if we're looking for a reduction, we can just read it right off the table because the table is reduction potentials. If we're looking for an oxidation, what do we have to do? Flip the equations and flip the numbers, positive to negative, because the table only lists reductions, not oxidations. Of course, we did that to save paper, right? It would have been the same all the same information just flipped around. So we can just do that. So they save paper by printing it only once. And every chemist knows that if A to B produces a volt, then B to A takes a volt. Right? So basically true. So what we did is we put a metal in a solution and another metal or another electrode in the solution. We check the solution and the metals for possible reduction reactions, and we look for the one that's the biggest number. Then we check them all for possible oxidation reactions. And for some of them it's the same reaction, just flipped. And we look again for the biggest number. Right? Be it positive or negative, it's still the biggest number. -1 is a bigger number than -2. Right? We've lost less money, so it's a bigger number. And then that tells us what's the oxidation number, what's the oxidation reaction, and which is the reduction reaction. Question?
When the aqueous salt is going to one side.
Let's wait till we get there. Let's finish this. Okay, so now we know that one of these will be the anode, and the other one will be the cathode. Red cap. The cathode is the site of reduction, the anode is the site of oxidation. The electrode on the anode side, if it is the electrode that's reacting, will disappear on us. The electrode on the cathode side will appear on us, will get larger. As we go, the solution gets depleted with ions. This solution gets depleted with ions as they join the cathode. This solution becomes full of ions of the opposite of one charge, a negative charge, if we, a positive charge if we disintegrate the electrode. So on this side, the solution is constantly becoming more positive as the electrode disintegrates. This side, the solution is constantly becoming more negative as the electrode augments. That can't happen. The solution cannot become negative or become positive. So what we do is we add a salt bridge, and the function of the salt bridge is to release the ions we need. On the anode side, where oxidation is occurring, we've lost electrons, so the solution is becoming increasingly positive, so negative ions will migrate out of the salt bridge. On the cathode side, the solution is becoming increasingly increasingly negative because we're adding electrons to it. And so we're pulling positive charge out of the solution. The solution becomes increasingly negative. Obviously, positive charges will migrate out of the tube. Question?
When, let's say, the sodium is traveling into the anode side, as the sodium ions are traveling in, are they transferring electrons? Is like
No, they just show up as ions. Yeah, they're just there.
there's no
One way of thinking about it, I used to think of it as it gives the electrons a way to sneak back. It's the charge that's going back, not the electrons themselves. The salt bridge just passes ions, not electrons.
So the sodium just shows up.
It just comes out of the tube. One sodium, as the solution becomes ever so slightly negative, that much sodium gets attracted in. And so literally the ions will just migrate because of the charge gradient. As soon as there's any charge gradient, the ions will migrate. Because they're bouncing around anyway, they're aqueous solutions, so there's free ions. There's a charge gradient, in other words, there's a slight negative charge here. The sodium ions will experience a slight attraction there, and they'll just migrate out as they bounce from water molecule to water molecule. Yes?
Does the salt bridge have to go in right in the beginning, or can you put it in after?
You put it in right at the beginning, because your cell won't run without it. As soon as just a few electrons go across, you create an imbalance in charge. You create an imbalance in charge, it stops right away. Electrons don't willingly approach a negative charge. So you have to constantly keep the solution neutral. So even the slightest charge gradient, ions migrate to neutralize the charge gradient, and the electrons will keep coming. So you put it in right away. In fact, the cell doesn't run until you stop the salt bridge. Because so few electrons can go without the salt bridge that you won't even register. Yes?
The cell will run so long as you have sufficient.
Yes. Sufficient anode or cathode, in this case anode, if it's the anode that's being oxidized, it could be the solution. Right? So as long as there's anode left, the cell will run. As long as there's solution left to contribute ions, the cell will run. As long as the salt bridge is not exhausted, the cell will run. If any of those things doesn't happen, then the cell stops.
So I don't need to start with any.
Any particular concentrations or anything?
No, sorry. Like the strip of gold I have.
Yes.
How much do I need?
Almost none. You need the tiniest little bit of gold. In fact, it doesn't have to be gold. Right? Because gold will pull the electrons. You can make this strip out of iron. Right? Gold will still pull the electrons because it has a much higher reduction potential than iron. So gold will pull the electrons in. You would have a piece of iron inside a piece of gold, which means you could electroplate iron with gold using this cell. This is not how we do electroplating. Usually we give the electrons an even bigger encouragement to move, but this would work. This would work.
Mr. Blenman.
In fact, actually, what would happen if you put a piece of iron into a gold solution, the iron would dissolve and the gold would become solid. Right? Because the gold would take the electrons right off the iron. So that would be a poor choice, actually. You see that? The iron would give up its electrons to gold right away, so you would have no electrode. The gold would go right to the iron, take the electrons from the iron, right, and become solid gold and probably just fall because you would eat away the iron. So iron would make a poor choice of starters. Platinum or another piece of gold would make a good start. You see that? If you put iron into a gold solution, the gold will take the electrons from the iron, and the iron will disappear, and solid gold would appear. Because gold likes electrons, it likes it more than iron does. So you can't put an iron electrode into a gold solution, that wouldn't work. You could put a platinum electrode in, or a gold electrode in. Questions?